Hey gang, there were a couple of problems I saw in lecture quiz 5 that some people were having, and I just wanted to make sure that I went through a couple of these problems to kind of give you some examples of them. So I'm going to quickly go through these. Question 5, 6, 7, 8, 9 were sort of problems for some people, but mainly for small reasons. We'll talk about that in a minute. And then question 12. Question 5, you might have had different numbers or something on your test, but for each one of these you might have slightly different variations, but that's okay. The process works the same. So in this one we got Rachel worked 3 part-time jobs in a week, and at one job she worked 20 hours at a salary of $12 per hour. Another one she worked $10 at $15 per hour, and a third she worked at 12 hours at $10 per hour. All right. What was her mean hourly wage? This one, if you treat we want to treat the number of hours as the actual weights, because that gives weight to how much money she actually made, and use the dollar amounts or the average that she made per hour as the data values, as the formula uses. Then we would do something along the lines of this right here. Where we've got the sum of W sub I, the weights times the data values X over the sum of the weights, and it's a pretty simple process here. So I went ahead and wrote those values down for us so we don't have to go back and forth as much. And if I do this correctly, then I'm going to take the weights, which are the number of hours worked, so 20 hours at $12 per hour, plus 10 hours at $15 per hour, plus 12 at $10 per hour, and I'm going to double check myself, make sure that was correct. 20 goes with the 12, 10 with the 15, and 12 with the 10, so we're good there. All right, and then we divide that, whatever that comes out to be, by the sum of the number of hours that she actually worked, so 20 plus 10 plus 12. All right. If we get that, and just throw that into our calculator here, 20 times 12, come on man, plus 10 times 15, plus 12 times 10, which is just 120. We get 510 total hours, divided by the sum of 20 plus 10 plus 12, so it's 30, 42. And that tells us she made roughly about $12.14 per hour on average over the course of the 3 jobs. So that one's just a matter of just knowing what the weights were versus what the data values were, or if you might have just made a slight calculation error somewhere when you were working through it, that was possible as well. All right, so we're on look at question 6 real quick too. This is one of those problems where you basically have to use the idea of an average to find a missing data value that should be in the sum in your numerator. In this case, we've got Addison, and she's been told that her average on 6 homework assignments in the class is 70, and she can only find 5 of her original assignments and wants to know what the missing score was. And so I don't know when this would really happen in real life, because most of the time your instructors are pretty good about putting all your scores in places where you can see them, but you never know. So we know that 5 of her scores are 91, 72, 66, 78, 75. And we need to figure out what the score was on her 6th assignment that she's missing. So, got that information here. So basically what we need to do is set up an equation, much like just using the idea of how we would compute an average. So we need to take these 5 values and sum them up. 91 plus 72 plus 66 plus 78 plus 75. Plus a missing value of X, we'll just call it X or whatever you want, and we divide that by 6, and that's supposed to give us an average of 70. So we're just really looking to find that X value. So we need to sum up those values first. And 91 plus 72 plus 66 plus 78 plus 75 should give us a grand total of 382. So we can simplify that down into a much nicer looking equation. And then multiply both sides of this thing by 6. That'll cancel out the denominator over here on the left, and we get 382 plus x equals 420. And then we subtract 382 from both sides. And that should give us x equals, I believe it's 38. Double check myself here. So 420 minus 382 is 38. Now you may have had a different set of numbers or whatnot, and you might have got a different answer here, which is fine. But this is the process you go through on any kind of problem where you're looking for the missing data value, but you know the average. So that was question 6. What about question? The next one I want to do was question 7. This one was a little bit more difficult, but it's still revolved around kind of a similar concept from question 6 and in computing a mean. And so here we're given information about two different statistics classes, section A and section B. So section A had 25 students and section B had 35 students. All students took the same final exam, and the mean score in section A was 72. We're not given the information about the mean score for section B, but we're told that all 60 students combined had an average of 79. So we're given that information. So I know some of you had a different version of this where you had 75 students in both sections. This process will work the same as well, regardless of what numbers you had there. So in section A, we got 25 students. Their mean score was 72. Section B, we have 35 students. We don't know their mean score. That's what we're asked about. We also know that all 60 students had an average of 79. So if you stop and think about it for a second, section A alone, looking at the 25 students had a mean score of 72. Let's just suppose that all 72 students, all 25 students made a 72. If that were the case, then the average would definitely be 72. Because if 25 times 72 divided by 72 would give us, divided by 25 would give us 72. So, in other words, what I'm saying is if you take the number of students in the class times the mean score and divided by the number of students, then those cancel out. You still end up with 72. So that's kind of the trick we want to use when we think about this thing overall. Let me erase that. All right, so the way I would set this up would be as follows. In section A, I know I had 25 students times 72 was their average. Plus, in section B, I had 35 students, but I don't know what their mean score is, so I'm going to call it X. So it's very similar to kind of the problem we did before this. This is going to be divided by the total number of students in both sections, which will be 60. 25 plus 35. So it's kind of like the students are your weights. All right. And then the average that all 60 students got was a 79. So again, this is just us having to solve for X. So if I do 25 times 72, I'm going to get 1800 plus 35x over 60 equals 79. Multiply both sides by 60. That kills this out. I have 1800 plus 35x equals, I don't know what 79 times 60 is off the top of my head. If you do, you're better than me. 4740. And then we just got to do a little bit more simplification. I'm going to subtract the 1800 from both sides because it doesn't have an x involved in it. All right. Now I'm going to get 35x equals, let's see, 4740 minus 1800. 2940. And I'm going to divide that by 35, the number of students in section B. And we'll get that x equals 84. So section B students averaged an 84 overall. So that's how you figure that one out. So again, it's very similar to the weighted problem that we did before. Question 8 and 9, I just want to make a mention about something really quick. Both of them revolved around you finding the variance and the standard deviation. Question 8 asked you to find the sample variance and standard deviation, and which sample uses for the variance is s squared. It's always the bigger number. When you use your calculator, like I taught you probably in lecture, to calculate, it's going to give you just s, and it's usually called sx. That's the sample standard deviation. You have to recognize the symbols because they get you in trouble really fast if you don't. So that's something I wanted to point out that was important for the sample. Now the population question, which was question 9, you still run the same procedure in your calculator, except for you look for a different symbol. You look for the variance, it's noticed as sigma squared, this little Greek symbol sigma. And for the standard deviation, which the calculator gives you the value for directly, is sigma. So it'll always, the standard deviation values, which are these guys here, let's call it SD, and these are the variances. The calculator gives you these guys, and then you square these guys. Some of you guys got that right, but you put them in the wrong boxes, which means you didn't recognize the symbols and their importance. It is important that you recognize symbols in statistics. As soon as you don't, you run the risk of making huge mistakes. So you got to be careful with that. The only other issue I saw in these problems were some people didn't pay attention to the directions for rounding the standard deviation and variance. I think I asked for the variance just to be rounded to 1 decimal place, but the standard deviations to be rounded to 5. So just pay attention to the rounding rules. I gave some points back on some of those if you just rounded wrong but had the right answer for people who did that. So just be wary of that. The last one was question 12. I saw some people have issues with that as well. Not everybody did. And I've got kind of everything laid out here. In the version of the quiz I'm currently looking at, question 12 is all about the empirical rule and Chebyshev's inequality. Get it up here. There we go. And so we'll go through this whole thing, but you're given some information here about 621 babies in a study done by the University of Chicago in birth weights. And the mean weight for these babies was 3,234 grams and with a standard deviation of 871. The next sentence says, assume the birth weights are approximately bell-shaped. So when you see that terminology, you can start thinking, well, I might be able to use the empirical rule here, especially when the first question says, estimate the percentage of newborns who weighed between 1492 and 4976 grams. We're not using, for those of you who know the normal CDF function, we're not using that here. We'll probably use that in some other things later in the semester. But for now, we're just going to do the approximations based on the empirical rule. So the quick way to start this out is just take the mean and the standard deviation and draw yourself a standard normal curve. All right, so I got the questions all written here for each part. And what I did is I took the mean, stuck it in the center, and then I took the value of 871 and I added it to 3234 to get to this middle mean value here to get the 4105. Then I added 871 to that value to get the next standard deviation unit above, which is 4976. And then I did it again to get it to 5847. And to go below standard deviation units below, I always go 3 standard deviations below and above when I draw this out. So I subtracted 871 from 3234 to get 2363, and then subtracted it again from that value to get 1492, subtract 871 again to get 621. And then I just jot down here my empirical rule, the ones that are coming from the empirical rule. It says within 1 standard deviation unit above and below the mean, with 68% of your value should fall between that. If you're 2 standard deviation units below and above the mean, it's 95%. And if you're 3 above or below and above the mean, then it's almost all, or 99.7%. Okay. Then what I did in here, and I think I might have shown this in lecture 2, I broke these down into smaller percentages, so if we get questions that don't follow strictly 1 unit above, below, 2 units above and below, so forth and so on, that we can calculate whatever percentages we need. And so that 68 cut in half is 34 in this section, 34% in this section. If you take 95 minus 68 and cut that in half, this is where you get the 13.5 from. All right, which is like 27, I believe. And then what you're left with in the tails, we don't really use the third one out here when we're breaking these down in this case. I don't worry about the 99.7, we don't get that exact. But the rest of everything left in the tails here beyond 2 standard deviations below is 2.5% each on each side. And that just comes from taking 95 minus 100% and cutting that in half, which cut 5% in half, you get 2.5. All right, so percent between, now to answer the questions, I can answer every question on here with this, with the exception of part E. But part A said, find me the percentage of weights that were between 1492 and 4976 grams. Well, 1492 is here and 4976 is here, so that's 1, 2 above, 1, 2 below. All right, the mean, so that means that I'm 95% of my data falls there. Okay, so let me undo all that red marking there so we can, it's 95%. Between which two values will approximately 68% of the data fall? Well, we've already drawn it out here. I'm actually pointing directly at them here and here. So between 2363 and 4105. And it is important we put them in order from smallest to largest. And then part C says estimate the percentage that weighed more than 2363. So more than this value right here. So we really need to add up all the percentages that I have highlighted in blue from here all the way back up, right? That weighed more than 2363 grams. So that'd be adding 34, 34, 13.5, and 2.5. Or you could do take 100 and subtract 13.5 and 2.5. Either way you want to do it works. But we take the 34 and 34, which is just 68, plus 13.5, plus 2.5, and we get 84%. The weights fell above that. Part D asked us to estimate the percentage that weigh between 1492 and 3234. So let me undo a few things here. This was 84%. So between 1492, which is here, and 3234, which is here, would just literally be us adding up the percentages between here and the mean, and that's 34 plus 13.5, so that should be what, 47.5% of the data fall between those two weights. All right, and that's the only thing, that's the only ones I can answer using the empirical rule. Part E starts out by saying if the data isn't bell-shaped, what percentage of newborns weigh between 1492 and 4976. Let me write that number back down here for y'all. Well, if the data isn't bell-shaped, then we have to use Chebyshev's inequality. And the question is, how many standard deviations units are we above and below the mean at those two specific values? Well, again, just like in part A, we're 1, 2 above and 1, 2 below. So Chebyshev's inequality, remember, is 1 minus 1 over k squared, where k represents the number of standard deviations you are away from the mean, in this case 2. So if we do 1 minus 1 over 2 squared, it gives us 1 minus 1/4, which is just 3/4. And in Chebyshevs, or percentage-wise, this would be equal 0.75 or 75% of the data falls between those if it wasn't bell-shaped. So the answer for this last one would be 75%. If we'd gone out all the way to 58, 47, and 621, that's 3 standard deviation units above and below the mean. We just replaced that K value with 3, and we ended up getting something, I think it's 8/9. 8/9, I'm pretty sure, is like 88.9%. Yeah. Multiply that times 100 and round off to 1 decimal place. It's like 88.9%. So, but anyway, I just wanted to go through those real quickly. If y'all have any questions or whatnot, please come to, feel free to email me, ask me things. I'm here for you. I haven't met anybody other than Steph in the Q&As, so, stop by and see me. I'd love to talk to some of you. Anyway, hope y'all are having a great one, and take care.